Shall we start? So, hello everyone. Thanks for still being here. Hope we still have some people at the end. So I've realized, to my great surprise and shock, that you guys have a ton of material for Friday's TA session. So of course there was the fact that last TA session was for just going over the exam, but still I didn't think there was that much material seen in between. So yeah, you have a lot. So it looks like you won't have time to probably see all of it. So probably some of it is going to spill over to the next TA session. All right, and in terms of material, yeah, we're doing quite well. Actually, we still have a bunch of time, and we're yeah, chapter 9 is the next and last chapter. So what I'm obviously going to do is not add chapter 10. That's good enough for the final. But probably going to go over more of the exercises, and hopefully if you have things that were less clear, you can ask me and I can go over them in class. So the goal is to learn very well. And thing is, if we go over stuff quite quickly, you may think that my explanation is so clear that it's perfect and you grasp everything, but then you go back home and maybe it's not, you forget stuff. So it's good to see things many times. All right. Second derivatives. Yeah, let's start with this. Oh no, yeah, let's just have a small example. So finding critical values. So just to get us started, so if we have f of x equals 1 plus 1 over x, where of course x is not 0. So find the critical values. Oh, I'm sorry. What I wanted to write was x plus 1 over x. Well, anyways, we could. This is more interesting. Could do the other after. But... So somebody has found them. No. How should I proceed? How did we find critical values? What is the important thing? Yeah. Exactly. And did you did it yield some interesting results? Yeah, right. Awesome. So fine. The derivative, set it equal 0 and solve for. Let's just do that. F prime of x equals, this is 1. This is minus 1 over x squared. Again, x must not be equal to 0, so that's good. And I set this equal to 0. So then I find that 1 over x squared will equal to 1. X squared will be equal to 1. So x will be equal to plus or minus 1. Okay, so what does that look like? I think I have the graph here. That one. Okay, so how do we know which is a maximum and which is a minimum? Okay, so I have it here, and I know that -1 and +1 are indeed my critical values. And I can pretty much see that here -1 is a local maximum and +1 is a local minimum. But how would I have known that if I didn't graph my function? X is? Yeah, this? X not equal to 0, yes. Yeah, so it means that, yeah, this domain, this part of the domain is cannot. So that's not a critical value. That's just a value that's not part of my function. So how do I know whether I have a minimum or a maximum? Yes. Yes, I could totally do that. So I could check what is the derivative. So this is my derivative. So I could check whether if I plug 1, I get 0. But then I could plug like 1.1 and then minus 0.9, for instance, and look whether it's negative on one side, positive on the other, or positive, positive, negative, negative. But that's not something that's fun to do. For one thing, because what is a small change? You would have to look at maybe 0.0001 plus the value. So yeah, in fact, in all actuality, that's not what how we find maximum or minimum or inflection points. There's a much cleaner way to do it. It's looking at the higher order derivatives, especially at the second derivative. So the second derivative, what is it? Well, it's the rate of change of the derivative. As we've said before, f prime of x is a function of x, just like f of x was. Yeah, so just for those who just joined us, we started with this function and we wanted to find the critical values. So we took the derivative and set it to 0. And we found that the critical values are plus or minus 1. So this is what this function looks like. And so since this is a function, then there's nothing that tells us that we cannot take a derivative of this new function. And what this new derivative is going to show us is how does the derivative change as x increases or decreases for any value of x. And especially, what am I looking for? Well, I know that so take, for instance, -1 here. So I know that if the derivative is positive on the left-hand side or not left-hand side, but the left side of the critical value and negative on the other, then it must be the case that the derivative is slowly decreasing, 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 right? It was positive, but then it became smaller and smaller. It became 0, and now it became now it became negative and even more negative. If you look at the maximum, then the opposite is happening. So you start with a derivative that's very, very much negative. The slope is going down. And then it's becoming less and less and less and less negative until it's 0 at 1. And then it's continuing to be positive and positive and positive. So what does that mean? Well, what you want is to check how is the derivative changing at 1. So what is the sign of the second derivative? If the second derivative is positive, then it means that I'm in this situation where the derivative is increasing all the time and even at 1. And if the second derivative is negative, then it means I'm at the maximum. All right. So now let me just say more about the second derivatives. So second and higher order derivatives. So in general, is possible to take derivatives of a function f of x many times. So how am I going to note them? Well, I have f of x. This is the 0th order derivative. I don't take a derivative. Then I can take the first order derivative. So it's what we've been doing so far, f prime of x. But then how I would note it with the same notation, I would just have f prime prime of x, then f prime 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 of x. And then at some point I have too many little primes, so then I would write something like f, I think it's 4 of x. So saying I take four times the derivative, I can take it as many as I like, as long as it's acceptable to take it. So let's look at an example. So, a nice polynomial function. So I have y equals, well, not y, just f of x equals 4x4 minus x cubed plus 17x squared plus 3x minus 4. And now let's go ahead and take the derivatives. So first order derivative. F prime. So I'll just give you a couple seconds to do it. So that's not this, of course. We're going to change it. So how many terms do I have in the first derivative? Yes, 4. And what is the intuition there? Well, the intuition is that if I'm interested in, say, the slope of some function, then whether that function is here on the y-axis or a bit higher, it doesn't matter. The slope doesn't change. So that means that the constant term is always going to disappear. So I'm going to, yeah, if it's a polynomial function, so I'm going to lose the constant term. Well, in any function, if I have a constant term, I lose it. So let's do that. This gives me 16x cubed minus 3x squared plus 34x plus 3. And this is my first order derivative. Then my second order derivative, giving you some time to do it. Well, actually, it's it's a pain to do it because the numbers get big. So let's just do it together. So 16 times 3, it's 48 x squared minus 6x plus 34. And I could go on. So let's see third order. Oh, so that's f prime prime. Then third order derivative, I would have something like f prime prime prime, which would be, this is 96 x minus 6. And then since we're so well started, let's continue. Fourth order. So 4 here. Oh, I remember why I wanted to write it in some other way. So let's have y equals this. It's just that I want to show you what the notation is. All right. So here I would have dy dx. Yeah, sorry if I'm messing up your note. And then what is the second derivative? All right. Well, the second derivative is taking the derivative of this object, which is itself a function. So it's dy dx dx. So what is dy dx dx? Well, I can just take the d and put it together with this other d, and then put this dx and put it together with this other dx down there. So what I would get is the square y over dx dx, but then I write it just dx squared. All right. So this is perfectly fine too. It's actually this is somehow more precise because here we really keep track of everything that we did. And then the third derivative, I would get just the same thing, but q, dq dx, dxq, dqy, and then sometimes people don't put parentheses here, but know that they are there. So it's wrong to write it this way because this is the x cubed, so that's not what we are doing. The d is cubed and the dx is cubed, right? Okay, so am I good? Oh yeah, so this is just 96. And then what's the fifth order derivative? What would I get? 0. So e5 y dx5 equals to f5x equals to 0. And then what's the sixth order derivative? Well, it's d6y dx6 6, and it's 0 again. And then it can go on as long as I want. So here, for nice polynomial functions like this, I can take as many derivatives as I like. And so this is going to lead me to introduce a concept I'm sure nobody among you have seen, but I still think it's a interesting concept, is the concept of smoothness, because you're going to hear about it later if you continue your studies. So what is smoothness? So imagine that I show my skin and people say, oh, your skin is very smooth. What does that mean? There's no wrinkle, okay, no bump. So it's all about being able to, yeah, so having no bump or no jump or anything. So in mathematics, it's very intuitive. It's all about being differentiable. All right, and the more time you can differentiate a function, then the smoother it is. So smoothness. So first thing to say. So smooth function is a continuous one, so it's continuous. So if it's discontinuous, then no hope it's not smooth at all. And so that's the first condition. So if it's not smooth, not continuous, there's just you stop there. And then if it is continuous, then it can be smooth. So what is smoothness? So smoothness refers to the number of derivatives which can be taken in the whole domain of a function. And so I'm just going to wait for you to write. So here, would this be smooth? Well, if I say that the whole domain of the function is the whole reals, then absolutely not, because this is totally discontinuous. But since I've said that, by the way, this isn't zero, I exclude x equals 0. Okay, let me not make a stupid mistake here. Yeah, okay, so it works. So it's since I exclude 0, so it means that I can take a derivative for every point of its domain, and that the function is smooth. But this is like a corner case, so shouldn't worry too much about that one. Okay, so let's go with some examples. So f of x equals to absolute value of x. So is that continuous? No. So I have some other opinion. Is it continuous? Continuity is I can draw it without lifting my pencil. So yes, it's continuous. So it is continuous. But can I take a derivative at x equals 0? Absolutely not. So non-smooth, well, not differentiable. At x equals 0. So not smooth. So we note it C0. Okay, so that's the notation for smoothness. It's C0. I have a picture of this function. No, I don't have it. Okay. So, oh yeah, but I think it's possible to find the y equals. I think it's ABS, right? Yeah. All right. No, wrong. All right, so you see it's continuous, but here the derivative does not exist. And here a polynomial function So like, for instance, f of x equals 3x cubed, 3x squared plus 34x plus 3. So is it continuous? Yes, no? Yes, yes, I see yes. Is, is continuous. Is it smooth? Yes, and even more so, it's where we can say it's infinitely smooth. So we note it. See, oops. Because we can take it can differentiated over domain and infinity of. Okay. And now the tricky one. So it's not easy to find a function that's not infinitely smooth. A lot of them are infinitely smooth. So the ones that are not infinitely smooth are like this one that we define, that we sort of define it by section. We say it's minus x over this section of the domain and plus x on this section of the domain. So you can see that more or less you have to define them by section if you want something that can be differentiated only a certain number of times. So you're not going to encounter too many weird functions in the wild, but I can show one to you. So let's look at f of x. Or you're going to encounter one in the not the exam, but the I haven't written the exam, so maybe, but in the homework, I think. So yeah, let's do this. Where is it? So let's say I have x squared, and I have like 0 here. This is for x is smaller than 0. And this would be for x is greater or equal to 0. So how smooth is it? So now pay attention, because this is a bit tricky, and you really have to do it this way if you want to find the right answer. So let's go ahead. So step 1. Is it continuous? So I just let you check it for yourselves. And the thing is, you have to remember what is the definition of continuity. So I'm just going to tell you. So at a certain number, so here, of course, the critical number is 0, right? Otherwise, there's no issue. So at 0 is the limit of the function going to 0 from the left equal to the function at 0 equal to the limit of the function coming from the right. Yeah, so I think I better do it with you, because it's not. I think we did it once, but still, let's do it again. So check whether it and x 0 from the negative section. Yeah, that's very small. I'm going to try and make this. Yeah, we can see better. Okay, so whether this limit of f of x is equal to f of 0 is equal to the limit when we come from the right. This is how you write it. So the limit when we come from the left is, well, now we have smaller values than 0. So we take this section. So it's essentially x squared. We have to take. So this is an easy limit. You just substitute 0 there, so you get 0. Right. Now f of 0 equals. Well, now the question is, which do I take? I said that if the x equals 0, then I take this section of the function, which is 0. So it's 0. And then let's take the right side of it. So the limit when x comes from the higher numbers, larger numbers. So I take again this section. So it's equal to the limit of this function, which is just 0. So it's equal to 0. So yes, it is continuous. Step 2. Is it differentiable? So first condition to be differentiable is to be continuous. That's the case here. Yeah, I should, how smooth is it? So yeah, I should have written, so the critical, or the, no, that's the problem with mathematics. So all of the terms are loaded. So the interesting, let's just say, value check is x equals 0, because otherwise that's pretty easy to see that. Okay. So now for that, somebody remembers what is the condition? We've seen this, I think, 2 classes back. Yeah, I'm happy to do that because maybe you don't remember the details. Anyways, it's not your fault. You had a midterm exam, so you were focused on more important things. Right, so my guess is most people are waiting for me to tell you what the answer is. So we check whether if I take the derivative with delta x coming from the left or delta x coming from the right, whether they are the same. So whether the derivative itself is continuous. So check whether limit delta x and delta x goes to 0 from the left of f of x plus delta x minus f of x. Let me just divided by x is equal to the limit when I come from the. So here it's not when x tends towards 0, it's from when delta x tends towards 0, but from still from the negatives or from the positive. And so in that, let's check that. Oh yeah, so of course at when x equals 0, because that's the number that interests me. So then I check whether this is the case. 0 minus f0, then 0. So this is the number that interests me. So this is what I'm checking. So let's do that. So this thing here will give me so when delta x goes to 0, but from negative values, it means that 0 plus delta x is some negative value, right? So in what section of the function am I? I am in the negative section of the function. So it's x squared that I take. X squared minus f of 0. Well, in which section am I of the function? When x equals 0, so I'm at 0. So it's this section. So what do I get? I get so this is 0, this is 0, and then I get delta x over delta x. And so I get, let's just simplify this. And then what is the final result? Limit when delta x goes to 0 of delta x is, have I lost most of you now? Okay, I said that limit when x squared goes to x squared when x goes to 0 is 0. So limit of delta x when delta x goes to 0 is 0. Yes. So 0 minus, but it's first 0 because we're going towards 0. So this is my left limit, but then my right limit is right. So now I have positive values of delta x. So it means that I'm going to have here f of some 0 plus delta x some positive values. So I am in this section of the function here. So what do I get? I get 0. So whatever is delta x, as long as it's positive, I know that the value is 0. And then what is f of 0? And again, I'm in this section, so it's 0. So 0 minus 0. So what do I get? I get 0 minus 0 is just 0. And so are they the same? Well, yes, 0 is the same as 0. So it's or derivatives are the same, and then their derivative exists. So I know that it is at least smooth of order 1 because I can take the derivative. But now let's not stop here. I'm just going to let you copy this. Yeah, so don't worry. I think in terms of like mental confusion, we're not going to more. Yeah, maybe some section of the class that are coming can be a bit tricky as well. But yeah, this is sort of the max, close to the maximum of that's just because I define stuff here. So you always have to check whether you're in this section of the function or that section of the function. So questions are too hard to formulate a question. So stop me if you're too lost at some point and you have a question. So I'm just going to go back and tell what we did. So we started with this function that is, well, actually I can show you the function, so maybe that helps. So I get f of x equals x squared when x is smaller than 0, and f of x is 0 when x is greater or equal to 0. So looking at the function, so graphically. So now I'm just going to show you everything, but we're going to explain the rest. So it's this one there. Right, so here I have x squared when x is smaller than 0, and just 0 when x is greater or equal to 0. And then, so this is perfectly continuous because it's defined everywhere, and it's so I don't have to lift my pencil to draw it. And as you can see, when I'm at 0, so there's no ambiguity, the derivative is 0. And if I were to evaluate it from this side, it would go to 0, and from this side, it would go to 0. But now we're going to look at the higher order derivatives. So because we don't know really if it's smooth or not, or we know that it's at least smooth of order 1, but let's look at higher order. So step 3 is the derivative differentiable. Why don't I care about the continuity of the derivative? Well, because I know for a fact that if I can take the derivative, then it has to be continuous. So I don't have to check it. I could check it and confirm that the derivative is continuous. You see that the derivative gives me this, and so it is continuous. But so let's see if the derivative is differentiable. So do you have an intuition as to whether we're going to get something differentiable or not? It's going to be? All right, so differentiable, it means, so this is f of x, so the derivative is this one, f prime of x. And for it to be differentiable, it must be the case that if I take the limit of the derivative from this side, I get the same limit as taking the derivative when delta x comes from this side, right? Here, if I take the derivative, I get something that's positive. Here, if I take the derivative, I get something that is 0. Yeah. So it's not going to be differentiable. And another way to express it is when I'm going to look at the second derivative. So here the second derivative is positive in that side. That's this value there. It's just always the same value because it's a constant derivative. But then you see that if I have a kink here, then it means that the derivative is essentially jumping. So it's yeah. So the derivative is not continuous, is not differentiable. So it means that the second derivative is not continuous. Here I have to lift my pencil to draw the whole thing. We're just going to confirm this. So how do we do that? So to verify, rules of differentiation. That's the simplest to do. To express x. Because it's yeah, it's a mess otherwise. So f prime of x on the negative side of x, then this is this part. If I take the derivative, I get x. And if I take the derivative on this side, I get 0. All right. Yes. So now let's again. So you know the derivative is continuous. Is it differentiable? So we check again the same thing, but with 2x instead. So let's look at this side there. So of course, always what I care about is so this will be equal to, so yeah, limit of f prime of x minus f prime of x. And I get what? I get, if delta x is smaller than 0, then it means that 0 plus delta x is smaller than 0. So I'm on the left side. So I take this, this function there. So I get 2 times 0 plus delta x minus, what is the derivative at 0? Well, it's 0 for delta x. So I get 0 disappears, 0 disappears. This, so what do I get? I get 2. So this it's already what I've seen there. So the derivative here is going to be 2. And now let's take the limit on the other side. So this is sign. And that's the same thing that I had before. So it's going to be equal to f prime of 0 plus delta x is going to be 0. And f prime of 0 is going to be again 0. So it's equal to 0. So we see that those two are indeed different. This is what we see here. The derivative is 2, and then the derivative is 0. So it is not differentiable. So the derivative not differentiable. Another way of saying this is that the second derivative is going to be non-continuous. So conclusion, what is the status of this function there? So conclusion is smooth up order. That's what I found. Yes. So why? Because I was able to take one derivative, but not two derivatives, right? So this is how you do it. And if I had found that this derivative was equal to this derivative, then what would we conclude? It's at least C2, but then we could check whether you can differentiate another time. So you would express f prime prime, and then do that again until you find that you cannot differentiate it. Yes. So that's a good question. So I allowed it last year, but so the reason why I didn't do it this way is in principle we could do that. So what you could do is use the differentiation rules and look at, but you would have to be careful. So what I'm saying is, let's go back to this this function here. Yeah, so here, since I said that x is not part of it, then we're fine. But if you just compare the limit of the derivative from this side and the limit of the derivative from this side. So here the limit of the derivative is, well, this goes to minus infinity. So the slope becomes infinitely negative. And what's the slope on this side? Well, it's also minus infinity. So it looks like it's the same. So it looks like it's differentiable, but it's absolutely not differentiable because you cannot even evaluate the function there. So yeah, I prefer being like very like strict when I do it. But in principle, you could if you know what you're doing, if you know that, okay, this point I cannot evaluate it, so yeah, you could do it. So just I'm going to rephrase what he's saying there is, rather than taking limits there, could I just use these things? Could I just use the derivative rules and check the limit of 2x when x goes to 0 from the left and the limit of 0 when x goes to 0 from the right? And then I would, of course, find something the same. Yeah, actually, I would find the same. So for the limit, so then I would conclude that it's differentiable. But yeah, I prefer doing it this way. Yeah. Thing is, at the exam, I'm going to be mindful of your time. So so this is more of the sort of thing that I can ask you in homework. So I know you have time to do it cleanly. At the exam, the trick is to do all the questions. Okay. So that's smoothness. What is it? Okay, yeah. So why do we care about the higher order derivatives? Now I've spent a lot of time on this, but so it's done. So let's go back to the higher order derivative. So conditions for extrema. So I said that, yeah, one condition for extremum is looking whether on the left of some critical point, or left from your perspective, the function has say a negative derivative, and on the right has a positive derivative. So let's use some more, some easier way of checking it. So use second derivative. So, oh yeah. So just before that. Oh, gee, I shouldn't have said that. I thought that I was here, but I had some other things to say before. Okay. Next class, next class. So interpreting the second derivative. So f prime of x, f prime prime of x means that slope f of x, oops, is greater than 0. Tends to increase. And is strict. Yeah, it's strictly convex. And the second order derivative being smaller than 0 means that the slope of f of x tends to decrease. And f of x is strictly concave. Now let me give you a definition of concavity. Yeah, before that, I'm just going to draw the function, so it's going to be very clear. Sorry for the graininess of the picture. Okay, so here, what is the value of the second order derivative? Is it positive? Is it negative? Over all of this function, what's the second order derivative? Is it? Yeah, negative, it's smaller than 0, or why? Because it always tends to decrease. So the function has a positive slope, but then less and less and less positive, and then 0, and then it starts being more and more negative. So the second derivative is negative. And in that case, we say it's concave. And what does it mean, concave? It means that if I take 2 points on the function, which I join by some segment, then the segment is, all of the points of the segment are under the function, are smaller than the function. So I'm going to express this mathematically. So for some value t, So here I have some stuff that I'm just going to use for my definition. So for some t between 0 and 1, and some x different than y, a function f is strictly concave so how do I express this? Well, I'm going to take the take some point between x and y. So some weighted average of x and y, whatever it is. So here it's here, for instance. And in that case, so a linear combination um, of f of x and f of y will be strictly smaller than the function at this average value t of tx plus 1 minus ty. So f of tx plus 1 minus t times y. So this, the value of this function, which is this one, is strictly larger than the linear combination of the two functions, the two values here. So is greater than t times f of x plus 1 minus t times f of y. Okay. So here's really you just look at have to look at the visual interpretation, and this definition makes a lot of sense. Or does it? I don't know. I don't want to speculate. So somebody has a question about this? So this really is a definition that I put upon you to understand. So that's concavity. And then, of course, I can have the same, the opposite. So also, a function is strictly convex if so rather than being greater, it is smaller. So you can imagine that then the function would look like the mirror image of that one. And then you could take a linear combination, and then it would always be under a linear combination of f of x and f of y. Okay, and now going back to what I was going to say. So for smooth function, for smooth curves, necessary condition that was nice. Necessary conditions for extrema using second derivatives. So for smooth curves, a necessary condition for a local optimum is that the derivative is equal to 0, f prime of x equal to 0. So that's the same as before. And now we have different sufficient conditions. So sufficient condition for a maximum expression there. What is the t? T is some value between 0 and 1. Some like 0.5, for instance. It's just some middle point here between to get some weighted average of x and y. Right, so that's just yeah, 0.6, 0.7, 0.2, right? For it. All right. And then we see that a sufficient condition for a maximum is that the second order derivative is greater is smaller than 0. Yes. But note the following. This is not sufficient. It has to be combined with that one. And so this is crucial. So if you just have the fact that if that the second derivative is smaller than 0, you could be here, for instance, and that's not a maximum. So what you need is that the second derivative is smaller than 0, and that the first derivative equals 0, right? So these are the two conditions that you need for a maximum, and sufficient condition for a minimum. Is simply that the second derivative is greater than 0. And of course, that the first derivative is equal to 0. Are we okay? So I can, do I have time to go back to the example? Yeah. No, let's leave it at that. We have seen quite a lot today. And then we can, next time we're just going to continue with the example. So yes, again, apologies for the length of the TD session on Friday. I told the TA you have to so start from the beginning, do as much as you can, but of course don't do too many exercises for each questions. I'm going to post the solutions, and then you can continue on the next week to do all of them. So for the homework assignment, you have, I think you have most of what you need really. With what we've done today, let me see what we still have to do. Yeah, no, we're really good for, yeah, you have most of what you need for the homework. And again, if you want to see it, so let me show you how you find it. So you click on homework assignment 3 and you get it here, the assignment. And it looks like this. Yes? Oh yeah, so I decided to give you quite a lot of time, so you have until Tuesday, April 12th. On me? Oh. Oh yeah, so let me change that real quick. Due date, yeah, April. Okay, now it's April.